Okay, so this video covers the second fundamental theorem of calculus, which is kind of saying the following. If you look over here, okay, this is an integral from some number to another number. So if you look at like any integral, for example, from 1 to 2, let's just keep the numbers simple of this integral. Well, what you're going to do is you're going to add 1 to the power, divide by that power, and you're going to go from 1 to 2. So you're going to have 2 to the third, which is 8 over 3, minus 1 over 3. You're going to have 7 over 3 for your answer. So what this is what I'm saying is that this is going to come out as a number. So this will come out as a number. So you can see right here. But the funny thing is that you can actually integrate something with a variable, right, on the top, and then it comes out actually as a function. So if we integrate this, well, little f, when you integrate, always becomes big F. So this little f would become big F, and you would plug this value in, right? And that's the basic idea of it. So that might not make a lot of sense. Let's do some examples that will make it a lot more concrete. So one of the biggest things about the second fundamental theorem is that you're basically saying that a derivative of an integral is the original function. So take a look here. If you take the derivative of the integral, they are going to more or less cancel each other out. Oh, wonderful. They're going to more or less cancel each other out, and you will have just the function on the inside. So let's think about this for a second. We have the derivative of something, and that something is the integral. So what's the integral of little f? Well, that's going to be big F. And you'd plug in the top number, which is x in this case, and now you'll have big F of a, right? Big F of a. So that's basically me. I anti-derived. What I'm trying to tell you is that I anti-derived this, and I don't know what that is because it's just function notation. I plugged in the numbers, and I subtracted. But now take the derivative of that. Well, what's the derivative of big F? The derivative of big F is little f of x. And the derivative of f of a, well, big F of a is equal to a number. It's a number. So if you take the derivative of that number, it's going to be 0. So if you derive this integral, you're going to get just the original function. Derivatives and integrals cancel each other out. It's the big idea. So let's take a look at this. If you were going to try to figure this out, there's a lot of things you could do. But the best thing you could do was be to figure out what f of x is. Well, f of x is, I guess, sine of x minus sine of 0. Okay? Why? Because I anti-derived cosine to sine, and then I plugged in the top number, and then I plugged in the bottom number, and I minus them, just like the regular fundamental theorem tells us. The cool thing is that now you know that sine of 0 is 0, so you have this function f of x, big F of x, is equal to just sine of x. And now what you can do is you can take all of these different options. So instead of doing 1, 2, 3, 4, 5 different integrals and plugging in this number every single time, changing it, now you have just this function that can tell you the answer every time. So we have just sine of 0 is the first one, right? And that's 0. And then you have sine of pi over 6. Sine of pi over 6, which is 1/2, right? 1/2. You get sine of pi over 4, that's 1 over root 2. I'm being a little lazy here. It's a pi over 4. And you can keep going. And let's just assume we've done that. So that's the basic idea of it. It just kind of helps us out a little bit. This isn't the most common type of example. This is probably a little bit more common of an example. This gets you the basic idea of it. So the derivative of an integral. What I'm telling you is that these are going to cancel out if this is a number. So if this is any number, right here, if this is any number, this is going to work, because when you antiderive and you plug in that number, whether it's 0 or 5 or whatever, that number is going to go away when this derivative comes into play and tries to run through the numbers that you integrated. So what's going to happen is that you're really just going to take this and replace with the x. So literally this equals the square root of x squared plus 1. They're asking you what is the derivative of an integral. When you antiderived, you plugged into an x, and then you took the derivative for x, so your answer is going to have an x. Let's go to some more examples. So here's another one. So this one's a little bit different because you see there's a x cubed up here. The only difference there is that you're going to need to actually take the derivative of that. So let's see. They want you to find the derivative of this. So they want you to find big F prime of x. They want you to take the derivative of this. We could go through this the long way. So why don't we start with that? Well, it's going to be sine, right? Sine of t, but it's going to be at x to the third minus sine of pi over 2. And this red thing is what we want to take the derivative of. So if we take the derivative of sine of x to the third, we get cosine of x to the third, but there's a chain rule going on here. That is 3x squared. So we have to multiply by that. And I'm just taking the derivative. So derivative of this, because it does say find the derivative. And now the derivative of sine of pi over 2, I don't care what that is, because that number, the derivative of that number is 0. So that's done. That's gone. So what you're left with is this as your answer. That's your answer. But here's what I'm trying to tell you. The shortcut is that you can still do your normal thing. You can take cosine, and instead of t, you're going to replace with the x, but not the normal x. You're going to replace with x to the third. And what's going to happen is if this is not x, it doesn't matter what this is. I don't care. Okay, so I don't care what this is. But if this is not x, you're going to have to multiply by the derivative of it. So that's 3x squared. And that is your answer. Could have done it the long way, of course, but we're trying to show you a shortcut that sometimes you have no choice but to use. So you're going to try this problem. What you're trying to think about is you've got this graph here, and you've got this integral, and you want to plug in these numbers. And if you take the derivative of this integral, what would you have? Well, g prime of x, right? If you took the derivative of that integral, you'd have just f of x. So that might be one really important thing for you to understand here, and I'm helping you out with the fundamental theorem, but this is how they use it, okay? Point of inflection, well, you're going to need f double prime, right? Oh, nope, you're going to need g double prime because they asked for the point of inflection on g. So keep that in mind. So you should be able to get this one. It's going to be a little challenging, but do the best you can do. And pause the video, give it a try, and I will be moving on to the next example. So we have enough time to do, I think, one more. So this is something that I think, I'm not sure if this is in the handout, but the net change theorem, what that's basically saying is there's really a couple of things that we need to understand. If you take this, right, and I've always talked about little f's antiderivative being big F. So antiderive this, that's big F, and then you plug in the top and you plug in the bottom. This is basically net change in something. So how can I make that more clear? What happens is often they ask you to integrate a rate of change. So if you're integrating, right, if you're integrating from A to B, the rate of cars through an intersection. Okay, let's say you're trying to integrate the rate of cars through an intersection, right? That's just going to be the number of cars at time B minus the number of cars at time A. I guess what I'm trying to say is the integral of a rate is equal to the amount of stuff. The integral of the rate of stuff, right, gives you the amount of stuff. That's what this whole big idea is about. So if I said, okay, well, how many cars go through the intersection, you would integrate the rate from that time period, from let's say 1 o'clock to 3 o'clock in the afternoon, and that would tell you how many cars go through the intersection. There was a pretty famous question a couple of years ago where bananas were being taken from a grocery store, and they said how many bananas were taken from the grocery store. Well, you have to integrate the rate that the bananas are leaving the store, which is some function they give you, and that will tell you the total number of bananas. So integral of a rate of stuff gives you the amount of the stuff. This one is not in your notes, I think, but this is a big deal, okay? This is huge, actually. You must decide whether you're being asked for a rate or an accumulation, okay? You're either going to get a rate of change or an accumulation of something. So there's going to be a lot of things going on with rate of coffee dripping through a filter, or the rate that Janet shovels her driveway, or the rate that gravel is accumulated on a surface. Now, those are all kind of derivatives, but if you want to know how much snow Janet shovels, that's an integral. If you want to know how much gravel piles up, that's an integral. So you integrate a rate and you get the amount of stuff. That's a really big point, okay, so don't miss that. Alright, so let's try this net change theorem. So here's the rate, okay, so they're giving us the rate. So I'm going to say the rate that the chemicals are flowing in is 180 plus 3t. So this is how fast the chemicals are flowing in. So at one moment there's 180 liters per minute coming in, and then a minute later there's 183 liters coming in, and then 10 minutes later there's 210 liters per minute coming in. That's how fast the liquid is coming in. It's like speeding up, it seems like. And they want to know the amount of chemical. Well, the amount of chemical is going to be the integral of the rate. So we're going to integrate that rate. And they say for the first 20 minutes, so when are we starting? What time? We would start at 0, and we would go until 20. And that's really all you need to do. That is a big idea. It's huge part of calculus. So really all you need to do is integrate that, and you should be able to do that. I'm going to stop the video here so we don't run out of time. So you're able to integrate that, I'm assuming.